Okay, so let us continue. Our second talk of the afternoon is by Ying-Ying Sun from University of Shanghai for Science and Technology, who will talk to us about elliptic KdV and KP systems.
Hello, everyone. I'm Ying-Ying Sun. Thank you for the introduction, and many thanks to the organizers of this conference. It's my first time to visit BIMSA, and I'm very delighted to have this opportunity to give a talk. This talk is based on a joint work with Frank Nijhoff, Dajun Zhang, Xinyi Wang, mainly on elliptic KdV and KP systems, which belong to a class of partial differential or difference nonlinear equations related to elliptic curves, which we call elliptic integrable systems. To be precisely in this talk, when we mention elliptic integrable systems, they are described by integrable equations when the dependent variable appears in the argument of elliptic functions, or where there are parameters that are essentially moduli of elliptic curves. Currently, there are not many examples for elliptic integrable systems, but they hold significant physical or geometric importance, like the Landau-Lifshitz equation and the Khrushchev-Novikov equation. What we are seeing here is the well-known Khrushchev-Novikov equation, which is a reduced equation from constructing exact solutions of a fundamental integrable system, the KP system. Cos A of x and t is a function of this equation, and we can see it appears in the Weierstrass elliptic P function. This function is defined by this formula we can see here. And j and j prime are integers, but they cannot be both 0 at the same time. If we consider the neighborhood of the point z is 0, it can be expressed in a Laurent theorem in this form. And we can also prove it has two periods, 2 omega and omega prime, 2 omega prime. Here, the coefficients J2 and J3 are coefficients and constants, which are determined by the periods. If we differentiate this result, when we can have its P prime, and we can prove P satisfies this differential equation. And we can see, in fact, P prime can parameterize the elliptic curve. And if we set P over omega is E1, P omega prime is E2, and P omega plus omega prime is E3, we can also have this relation. E1, E2, E3 are branch points of the elliptic curve corresponding exactly to the zeros of P prime function. Another common form of the Khrushchev-Novikov equation, or the Kn equation, is this form. And we can see Ru is related to the elliptic curve. So J2, it's a cubic polynomial, and G2, G3 appear in this form. By the identification U is a P of C, we can recover the original Kn equation. We say this equation is completely integrable by proving it possesses Lux pairs, infinite number of conservation laws, Hamiltonian structures, as well as exact solutions. In addition, Adler gave its Backlund transformation, which means from this transformation, one can get from one, say, the solution of the Kn equation to get another solution of the same equation. Let me explain this by this picture. So from a seed solution U, we can use the Backlund transformation with parameters little p, big P, to get another solution U tilde. Here, little p, big P satisfies the points on the elliptic is a point on the elliptic curve. And from the solution U tilde, we also use the Backlund transformation, but with another Backlund transformation parameters Q, we get another solution we call U tilde hat. Similarly, if we follow this path, from U, we can get a U hat and a U hat tilde. It can be proved that U tilde hat is equal to U hat tilde, which is the permutability property of the Backlund transformation. So we can have a nonlinear superposition formula for these four solutions: U, U tilde, U tilde, U hat, U tilde hat. And K0, K1 to K6 are coefficients of this formula, which are expressed by P, Q, J2, J3. So we can see the moduli of the elliptic curve in this relation. By identifying these four solutions, to regard them as a square lattice, as points on a square lattice. So we can regard this as n direction. N is integer, and this is m direction. So m is also integer. We can get this formula. We can regard this formula as a discrete equation. The discrete variables are n and m. So we also call this is a discrete Kn equation or Adler's lattice equation. This difference equation also appears, in the Adler-Babenko-Souris list, which contains 9 equations, and it is in fact a master equation in this list, because the remaining 8 equations whose names are written in these boxes, in fact, they are the special limits from the Q4 equation. This equation is integrable in the sense of admitting Lux pairs proved by Frank Nijhoff, and Hitterente gave another equivalent form by using the Jacobi elliptic function. Then we use its Lux pair to give conservation laws. Ramani, Joshi, and their collaborators considered its a periodic reduction to elliptic difference Painlevé equations. As we mentioned, the coefficients in the Q4 are related to the moduli of the elliptic curve. So we also regard Q4 is an elliptic integrable lattice equation, lattice system. As far as I know, there are only 4 classes of this kind of equation system. One is Q4. Another one is 3 proposals for lattice version of Landau-Lifshitz equation. But very little study on these equations. Even the relationships between these equations are not clear. The remaining 2 are elliptic lattice potential KdV and KP systems, which were firstly derived by Nijhoff and his PhD students by extending the classical KdV or KP systems to a generalized system related to an elliptic curve. Then subsequently, they also prove its integrability in the sense of possessing Lux pairs as well as multi-soliton solutions. Based on these results, we consider to rederive these systems and construct more types of exact solutions of these systems. Recently, Nijhoff, Dajun Zhang, and Cheng Zhang also revisited this system and considered the explicit structure of the tau function. Next, I'd like first to show you what is this system, or what this system looks like. So this is the elliptic lattice potential KdV system, which is 2-dimensional with 3 components. Here, you tilt hat. The notations still are the shift notations as we introduced before. A and B are lattice parameters, and the variables are U, S, and W. It's noted that in this system, we have a part related to the elliptic curve. So in this case, the elliptic curve is written in this form. E1 and G are the moduli of the elliptic curve. So for the first equation, we can see G is included in this equation. And for the 4th one and the 5th one, we can say this part is related to the elliptic curve. Here we see E1, E2, E3, as they were introduced before. And this elliptic curve can be parameterized by this formula by using PP prime. And when J is 0, the elliptic curve becomes a rational curve. And we see the first equation in this system, this one, cancels. So the left or the remaining equation is in fact the lattice potential KdV equation. That's also why we call this system elliptic lattice potential KdV. Next is the elliptic lattice potential KP system, which is 3 + 1 dimensional with 7 components and 7 equations in this system. Very complex form. We can see tilt, hat, dot, and bar are shift relations, shift notations. A, B, C are lattice parameters. So there's one direction without lattice parameter, which we'll introduce later. So as we mentioned, based on the results given by Frank Nijhoff and his students, we know the exact solutions is called soliton solutions for this system. We can use it to construct more types of solutions. And the method we employ is a generalized Cauchy matrix approach, which based on Cauchy matrix approach. So I'd like to introduce this approach first. The starting point of this approach is a dressed Cauchy matrix. So we can see M is this kind of matrix, and if rho I, Cj are equal to 1, this is a Cauchy matrix. But usually, rho I, Cj cannot be 1 because we'd like to connect this to the integrable systems, and usually rho I contains the information of the independent variables. For example, in this case, for the ABS equations, the rho I is defined by this form. We can say the independent variable are n and m, which can also be calculated in these relations. Here, rho I can be taken continuum limits to get the exponential function. So it's called the discrete plane wave factor. Oh, sorry. And from the element of the dressed Cauchy matrix, M, it is easy to calculate. It satisfies this relation, which is in fact the Sylvester equation. And here, K is a diagonal matrix, and RC are column vectors. T denotes the Euro transpose. Okay, and in this game, they give the tau function by defining it as the determinant of I plus M. I is the identity matrix. And also they give or define scalar functions as Ij. Ij are integers. It can be proved as Ij is symmetry and connects with the discrete integrable systems. For example, if we choose I is equal to j is equal to 0, we can prove S00 satisfies the lattice potential KdV equation or the H1 equation. And as we define the structure of Sij, so we also know H1 has a solution expressed by this form. So it is clear that C, by the way, C is a constant vector. So C is constant, and I, we know M is expressed by this form, and R expressed by this form. So we can write explicitly of the solutions. In this case, it's soliton solutions. Based on this work, Da-Jun Zhang and Songling Zhao considered its generic case, which means, last page. Okay, here K is diagonal, but their starting point is this Sylvester equation, and K is no longer diagonal, but an arbitrary matrix. And for R, we give an equation or dispersion relation on it, which is expressed in this formula. Of course, for the K, we give a condition, which is the eigenvalue set of K and minus K is empty. Okay. In this scheme, the tau function, Sij functions are also defined, and it can be proved the symmetry and its symmetry and recurrence relations. Also, in this case, when U is S00, they prove it satisfies H1. And in this case, we know K is no longer diagonal, so we could get more solutions for the H1 equation, which means not only Soliton solutions we can get now. And to derive the solutions, we do not, as we say, we could solve this Sylvester equation to get M and solve the dispersion relation to get R. And then for S00, we can know its explicit solution. But when we want to write out explicitly form of this solution, we consider we would like to consider all the cases of K, and to do that, they prove the invariance of the Sij function by introducing a transformation matrix T, and prove Sij is invariant under the similar transformation, as well as the Sylvester equation and the dispersion relations. So by this similar transformation, we only need to consider the canonical form of the K, which means we can only consider these two basic forms, the diagonal case and the Jordan-Bloch case. The general case, in fact, is a combination of the two basic cases. So in these three cases, or we can say the two basic cases, we can derive the solutions for the Sylvester equation as well as the dispersion relation. For the solution M, they give a factorization of this matrix. So here J is the Cauchy matrix, in fact. And also other cases, they also derive the solutions. The solution steps is concluded here. So from gamma, we use the dispersion relation, we get R, and then using the Sylvester equation, we get M, and substituting them to Sij, we get the solutions of the integrable systems. By the way, in fact, in this game, not only H1 is obtained, many equations related to H1, like if we set I is -1, J is 0, if we choose different integers of Ij, we can get different equations. And also, the relations between these equations can be derived in this game. So there are many applications for this game, like semi-discrete, we just introduced, and also semi-discrete and continuous integrable equations. For the elliptic lattice potential KP or KdV systems, we also employ this method by starting from a Sylvester equation written in the form 1. We can see here. It's more complex than the usual or the rational case. So here, M is the unknown matrix. PQ, big P, big Q are known and satisfy matrix relations too. Dispersion relations are on R and C are given by formula 3. So we can say the the lattice directions here are N, M, and L, while the direction M, there's no lattice parameter associated with because of the last equation in these relations. Okay. And we also give master functions of which are Sij defined by these formulas. Here C is a constant matrix such that I plus MC is invertible. And the tau function is given by the determinant of I plus MC. The main idea is from the dispersion relation 3 by using the Sylvester equation and the dispersion and the definitions for Sij, we can get the dispersion relation for M and then for Sij. The main results for the elliptic KP system are the following. We choose different integers of Sij like 0, 0, 0, 1, 1, 0, and so on. These are 7 variables which we saw them before. And we can also get its Lux triplet. As now, none of P, Q are similar to any diagonal matrix, we can get new solutions of this system. Also, we can do the dimensional reduction by setting N is equal to N prime, P is equal to Q, and C is the identity matrix. We can get the elliptic lattice potential KdV system. But in practice, this is not that easy to work out. So we start from the Sylvester equation for the elliptic lattice potential KdV system in the form 5. So here we can see, so K, small k, replaces the P in the KP case. And small k, big K satisfy this matrix relation. And also we give the discrete dispersion relations by the formula 7. Here C is regarded as a constant vector. So we only impose dispersion relation on R. We also consider the continuous elliptic potential KdV system by considering the continuous dispersion relations, which are given by the formula 8. So we can now say the independent variables x and t in this system. Also, we define the master functions Sij by 4 parts. And the main idea is similar to the KP case. Also, the main results are first, the symmetry property of Sij. By the way, in KP case, there's no symmetry property for Sij, as well as recurrence relations. By selecting particular integers for ij, we get the elliptic KdV system. And also we can get its Lux pair and new solutions. In addition, we do continuum limits for the lattice system to get the continuous elliptic potential KdV system. So, and we also show some dynamics of the solutions for the continuous system. So in the following are some details of this game. First, this is a recurrence relation for Sij written in a term. And if we would like to have these relations, we need 3 relations from the Sylvester equation. And also the auxiliary vectors are needed. From the Sylvester equation and the discrete dispersion relation, we can get the shift relation of M. So here, in fact, we can see the second relation can be derived by changing A tilde to B hat, similar to these equations. And also from these dynamical relations for M, we can get the dynamical relations or shift relations for Sij. Because there are 4 parts for Sij, so here the dynamical relations for Sij are also there are a number of relations for that. Then we consider to define U is S00 and SHVW in this way. And from the dynamical relations on last page, if we choose particular integers for Sij, we can get these relations. As well as, so here is about the shift relation with respect to tilde or n direction. For hat or m direction, we can get by just changing A to B and tilde to hat. And combining these shift relations and eliminating S10, S-1, S-1, -2, H, and V, we obtain the closed form of elliptic lattice equations of the variables U, S, and W. Several hours ago, Dajun told me this system can be rearranged as 2 equations with 2 variables. Also, we can get its Lux pair from the Cauchy matrix game by denoting the first element of U0, which is the auxiliary vector we introduced before. It's here L and N are 2 by 2 matrices. N can be derived by changing A to B and tilde to K. The compatibility condition phi hat tilde is equal to phi tilde hat can give us the discrete Lux equation, which gives the elliptic lattice potential KdV system. So this system is integrable in the sense of admitting Lux pair. And for the continuous case, from the Sylvester equation and the continuous dispersion relation, we can also calculate its evolution of M and Sij. For the higher order derivatives of Sij, we could use the computer software such as Mathematica to calculate. And from the evolution of Sij, we can get the elliptic potential KdV system. This is a continuous system. We can see there are 5 variables in this system. And for the first one, for the first equation in this system, if j is 0, so this term cancels. And the remaining is the classical potential KdV system, which can get the classical KdV equation. No, sorry. This system can also be arranged by introducing a capital A function, and it turns into this system with 2 variables, S and A. We can also obtain its Lux pair in this form. It's more complex than the lattice case. And for the exact solutions, as we mentioned before, in fact, the particular Sij, and we only need to solve the equation for M, K, R, C with the canonical form of gamma of small k, which means we only need to consider the equations 12. So the solution steps are similar to the lattice ABS lattice equations. From gamma we get k, and so from gamma we get the big K, and then we can substitute them to the Sylvester equation to get M, and for the dispersion relations we solve for R and C and substitute them to get Sij. The canonical forms of K are similar to the ones we mentioned before, and from which we could get the K. So for the diagonal case, gamma is a diagonal matrix, and also K is diagonal. Their elements satisfy all this relation. We can see K, small k, big K are points on the elliptic curve. Also, for the Jordan block case and the general case, we can have the solution for K, capital K or big K. And then we can solve the Sylvester equation for M to get this formula. So here we can see when j is 0, it goes to the ABS case. So it's elliptic, or that's also why we call it an elliptic intention of the lattice potential KdV. The Jordan block case, general case, we can all of them can be calculated. And for the dispersion relations, we say in the diagonal case, Ri is similar to the one we saw in the ABS lattice. But in fact, it's different because here, small k carries the information of elliptic curve. Okay, this is the solutions for the continuous dispersion relation. Here is an example for working on the dynamics of solutions for this system. We take the solution U as an example, as we mentioned, the U is S00, and can be expressed by this form. And it can be written out in this form. So here are the parameters of the solution. This solution, K1, big K1, is a point on the elliptic curve. And if we want to draw the picture, we need to consider not a potential one. So we take the derivative of small u to get capital U here. And we can calculate the top trace. And then we substitute the top trace to this solution to get the amplitude of this wave. Here are the photo pictures of the solutions. The first one is about the solution we just saw. So we draw the solution in the real form by considering J2 and J3 are reals, and kappa 1 should be real or pure imaginary. And the second picture, we show two soliton interactions. It can be analyzed that after interaction, the amplitude has changed. So it's not an exact soliton solution. So, but we can call it elliptic soliton solution. Or we can also do the asymptotic analysis to calculate the amplitude, the top trace of these two solitons. Okay, that's all for my talk. Thank you.
Thank you very much. We have time for a few questions.
Yeah.
Just an idea. To consider the generating functions of your master functions Sij. Have you done it if it appears some simplification of your analysis? Just generating function on two variables of your master function Sij.
Yeah.
Does it satisfy some quadratic equation, or have you tried to?
You mean for the general Sij?
Yes.
We didn't consider the closed form equation for Sij, but we could get many shift relations for it. And if we consider equations, we only consider particular choices of Sij.
Okay. Other questions?
Do you have, in the elliptic case, some pseudo-differential operator formalism developed?
Sorry?
Do you have some pseudo-differential operator formalism developed in this elliptic case?
No. No.
Okay. All right. Let's thank Ying-Ying again.
Thank you.